So, hi there. Now we're with the electrons. They're found outside the nucleus, right? And so they're found on these certain places called energy levels, shells, orbitals, clouds. And the number of these negative electrons, that's their charge, -1, is equal to the number of protons if this is an atom that is therefore neutral. Just as many negatives as positives. Electrons have the tiniest little bit of amount of mass, but they do have some mass. If a thing lost an electron, then it would become positive. It lost a negative thing. So if this is the symbol for sodium and it's lost an electron, we would call that a positive sodium ion. And the electrons we're going to focus on now are the ones in the outermost shell that are called the valence electrons. Valence electrons make an atom reactive. What does that mean? It means when it bumps into another atom, very simply, does it stick to it, bond to it, or does it bounce off? That totally depends on the number of valence electrons in the two atoms that bump into each other. In our chart here, our periodic table that you're familiar with, arranges atoms in terms of how many electrons are in their outer energy shell. 1, 2, 3, 4, and so forth. So here's the very simple rule. Here's the nucleus of an atom. An atom has electrons around it, number-wise, in very distinct amounts. The very first shell can have a maximum of 2 electrons. The second shell orbital can have a maximum of 8, and then 8, and then 8, and we're simplifying this just a little bit, but this is called the rule of 8. And if in its outer shell, so in this, that would be this third shell, an atom has a full number of electrons, which is 8, except if the outer shell is this one, it would be 2, then that atom is said to be stable. It's non-reactive. It's not likely to bond with something else. Soon, like right now. So what if you're sodium and you lost that one electron and that made you a little bit positive? You have a charge of +1. If you lost it to chlorine, why would you lose it to chlorine? Because chlorine is element number 17. So what does it have? It's got 2 electrons in its inner shell. It's got 8 in the next shell. That's 10. And then the other 7 are out here in the outer shell. What would make it very stable / happy? 1 more. What's more than happy to give it 1 electron? Sodium, if it bumps into it. If they get close enough, this transfer of electrons, there's a key word up there, this transfer of electrons will cause them to become both ions. What did chlorine become? When it got an extra negative electron, it became a negative. Particle is a good word now. Sodium now is a positive particle. Positive ion, negative ion. What are they going to do? This is one of the other things we've learned about our universe. If one thing has this charge that we have referred to as a negative electric charge and the other has a positive, they will attract. This force of attraction is called the electrostatic force. And the electrostatic force here will create a bond between these two, which is called an ionic bond. That's a good name for it because both of them are ions. That's why they bond, is because they have become oppositely charged ions. Now I want you to look at this in red throughout these PowerPoint notes. I'm going to put word for word straight from the EOC syllabus some things. And this says items, that means test items is what items means, test questions, will not refer to intermolecular forces found in the 4 types of macromolecules. We'll get to those other words later. Yeah, but they really are. And so that's why I'm bringing ionic bonds. That would be a intermolecular force if it was between 2 molecules, and it can be, as we'll get to later. And it's also something that is a big reason why things work the way they do. So anyway, this little package, just for strict nomenclature, naming, is not called a molecule. You could make a case it's 2 or more atoms bonded together, but the strict definition of molecule is two or more atoms covalently bonded together. And that's what we're coming to next. And I realize, again, at least I hope, all of you have had this, but you're getting a refresher. So what does covalent mean? Covalent kind of implies we are going to cooperate here or share, so to speak. So covalent bonding involves not a transfer of electrons, but sharing between two electrons. Sharing of electrons between two atoms. Why would two atoms share electrons? Well, this works in a way that makes sense, even though atoms aren't capable of thinking and making sense. In this case, they act like they are. So for instance, here I'm going to use oxygens as my example. Here I have two oxygens. Here's their nucleus, and they each have 6 valence electrons. They're element number 8. They have 2 electrons in their inner shell, 6 in their outer shell. Well, they would like to get 2 to make their outer shell full. 6 plus 2, 8. But if 2 of them bump into each other, neither one wants to give up 2 to the other. That makes them even more unstable than when they had 6. And so what happens is it's almost like they agree to share. Because if one of these oxygens will let the other one borrow 2 of its for a little while, those 2 travel around there for a little while, along with the 6 that this one has. 6 plus 2 is 8. But sharing goes both ways. And so if this oxygen is willing to share, and willing again is not a word we ought to use, is willing to share 2 with this one, that's only if that one will share 2 with this one. So at some point in time, those electrons that are being shared are around one nucleus, sometimes they're around the other, but this causes them to bond. What causes them to bond? Sharing doesn't cause you to bond. It might create an emotional bond between people if you share, and it does, but that's not the kind of bond we're talking about. So what's the nature of this bond? Once again, it's the electrostatic force, and I'm going to use hydrogens as an example. It's kind of a little simpler here. So hydrogens have just 1 proton in their nucleus, and then they each have 1 electron. And they would like to have 2, because that would make that inner shell full. But if 2 hydrogens bump into each other, again, a transfer of electrons would leave one of them unstable, unhappy, so to speak. But if they both shared, then they could both have 2 electrons, at least for a little while. So what would the case be if the electron that was traveling around this nucleus, but then got shared with this one for a little while? What if at one particular point in time it was over here, right where I left it? This electron being shared and this electron, which was here from the beginning, make 2 negative electrons and only 1 positive proton at this specific point in time. What's that mean? Effectively, right now, momentarily, even though we're not going to call it that, this is like an ion. It's got a negative charge. And what is this over here? Well, its 1 negative electron is now over here. So it's this lone positive proton all alone, meaning this has a little positive charge at this instant in time. What are these 2 doing? They're sticking together. They're sticking together. Why? Because of the electrostatic force of 2 opposite charges. So now this kind of shared bond, we actually have a specific symbol for, and it's very simple. It's a straight solid line. That solid line represents a covalent bond, but more specifically, it represents 2 shared electrons, 1 from each, right? We also refer to it as a single bond. Let's go back to our oxygen. Our oxygen was sharing not 1 electron each, but 2. So 1 pair of shared electrons, symbolized by a solid line. The other pair of shared electrons, this kind of bond is simply called a double bond, double covalent bond more specifically. And as you might expect, it's about twice as strong as this single bond. So Here we now get into, with water, especially with water, and this is with methane, a molecule also called natural gas, carbon and 4 hydrogens, right? All covalently bonded into one molecule. Now we get into another very important for biology aspect of covalent bonding, and that is sometimes the sharing is not equal, and water is your classic example. So if an oxygen atom with its 6 valence electrons bumps into 2 hydrogens, each with 1 valence electron, we have a situation that's good for sharing. With its six electrons out here, what does oxygen want, so to speak? 2 to make that 6-8. What do hydrogens want with their 1 electron out here? They each want 1, 2. Neither one wants to give up electrons. Both would like to have, so they start to share. Each hydrogen shares its 1 electron with the oxygen that will share 1 of its electrons. However, oxygen as an atom has a much higher attraction for electrons, a word that we call, I didn't write it up there, so I'll write it here, electronegativity. That is a measure of the attraction for electrons that a substance has, in this case an atom. And oxygen's got a pretty high electronegativity. It shares these electrons, but it attracts hydrogens a little closer to it. So in general, oxygen has around its area more electrons than protons. It's got 8 protons inside here, 8 of its own electrons, and the 2 that it's sharing with hydrogen stay a little closer to it, so that makes like 8 protons and 10 electrons, more or less. So the oxygen side is partially negative. That thing that looks like an 8 is actually the Greek letter gamma, lowercase, and for some reason we chose it to mean partial. We say this is a partial negative charge. This molecule that we call water has areas of charge. It's got 2 slightly negative areas, and then where the hydrogens are, that have that proton, that's electron is being kind of hogged by the oxygen, is slightly positive, 2 slightly positive areas. So this makes a water molecule very unique in a way that we use the word polar to describe. Because what the word polar means in many different ways is you have 2 things that are on like different sides of an object, the north and south pole of the earth. Personalities that are bipolar. Sometimes they're this, sometimes they're that. Those are the 2 places we normally see the word polar. Here we use it as a molecule that we call polar, and these bonds that we also call polar. A polar covalent bond is due to unequal sharing of electrons. Why does that result? Because one of the atoms involved in sharing has a higher electronegativity, attraction for electrons. So this is a chain of logic that we're going to come back to in our next little unit with water again and again and throughout the year. Here we find something. Why is it that way? Because of this. Why is that that way? Because of that. So here's what we find. We find that water molecules are polar. Why is that? Because between their atoms there is unequal sharing. Why is that? Because one of the sharing partners, oxygen, has a higher attraction for electrons than the other sharing partner. That leads to a polar molecule, and what water's polarity leads to is a big factor in how life works. So here in this content limit, they tell you that when they talk about properties of water, which are a big thing, they're only going to talk about hydrogen bonding, which we'll get to, polarity, which we just talked about, and cohesive adhesive behavior, which is about things sticking together. Well, here's what I said about that other content limit before. What is hydrogen bonding? Hydrogen bonding is an intermolecular force that they promised they weren't going to ask you about, except here they tell you they are going to ask you maybe about some particular intermolecular forces. So I think that might be the end of this particular set of slides, if I remember myself right. And next time we'll visit water a little more carefully, and working our way towards those big molecules where hydrogen bonding and polarity have a big effect on their structure and therefore how they work, their function. So, hope you enjoyed.